Hi everybody, and welcome to our next and last lecture on waves and sound. In particular now something called a standing wave. Now, as we've talked about, the various levels of waves. You have mechanical waves and you have electromagnetic waves. Okay? Mechanical waves require a medium, electromagnetic waves do not. Under the idea of mechanical waves, we have traveling waves and we have standing waves. Traveling waves, of course, are waves that travel. They go from one point to another. Of those, we saw there was a transverse wave, a wave that moves perpendicular to the medium as it travels, and a longitudinal wave, a wave that moves parallel to the medium as it travels down to the medium. Now, a standing wave, though, is a wave, unlike a traveling wave, it doesn't really go anywhere. It simply oscillates within the medium. And so that means that the medium and the wave itself kind of all stay in the same place as this thing moves around. For example, like plucking a guitar string. The guitar string, when you pluck it, it's a vibration, it's an input of energy. The guitar string vibrates, but the wave that's there just sort of oscillates up and down there. It doesn't really go anywhere. This would be an example of a standing wave. Okay, one that is simply like a guitar string oscillating up and down within the medium. Now there's some couple points to note that exist within this particular wave itself. First, there are locations on a standing wave called the nodes. And a node is a location where there's basically no real motion of the wave itself. So in this particular wave, the idea of a node would, for example, be out here at the end where it's fixed. Technically, this should be a node right here at this end, although that is moving quite a bit. It is a region where there's supposed to be a minimal amount of movement. So really, somewhere in here would be sort of another node. Okay, so a node is a point where we have sort of a minimal amount of movement. The next location on the wave is something called an antinode. And this is a point on the standing wave where there is a maximum motion. In other words, where the largest part of the amplitude is. Okay, so the point of nodes would be zero amplitude. The point of the antinodes is where we would have our maximum amplitude. So in this example right here, this central region right here that moves up and down around this equilibrium point the most, this would be where we would classify our antinode. So if we freeze the wave, notice here we have a node here, sort of a node out here, and the region of antinode right here in the middle. Now, one of the main features of standing waves is that they can produce traveling waves. So for example, a guitar string, as you pluck it, creates the standing wave. The traveling wave that is produced is the sound that you actually hear. And this is the way most musical instruments tend to work. Musical instruments tend to involve the creation of a standing wave, and in turn that standing wave will develop a sound wave that will travel from one place to another for us to hear. And that's really how we get music. Now, there are a couple different ways to produce standing waves. One, like a guitar string, is on a string itself. Now there's a couple of interesting things that affect the standing wave on a string. Anybody who has ever played a musical instrument knows that there are various things about stringed instruments that often occur. For example, one of the examples is on a guitar. All those guitar strings, if you look at them, are very, very different thicknesses. And the best way to look at it is some strings are very heavy and some strings are very light. So it turns out that the frequency of the guitar sound wave, the string standing wave, is going to be based on a couple of things. First of all, mass. Now again, for those of you who have played stringed instruments, you know that the heavy, thick strings produce very low notes. Remember, frequency is like the pitch, the note. So in other words, if mass goes up, that makes your frequency go down. Frequency goes lower. One of the other aspects, at the top of any violin, cello, any stringed instrument, guitar, there are these little things that you turn that will loosen or tighten the string. In other words, affect tension. And again, those people who are used to playing string instruments know that the tighter I make that string, the higher the note goes. So as tension goes up, frequency goes up. And then the last thing, well, one of the tricks on any of these stringed instruments to change the note is to press your finger down on one of the frets. And that essentially alters the length of the string. And again, for our stringed instrument players, they know that longer strings tend to produce lower notes. So as length goes up, frequency goes down. One of the ways to make a different note is you pinch down on the string, shortening its length, thus making a higher note. Now again, when a standing wave occurs, when a string is vibrating, there are a number of different things that can happen in terms of how the string is actually going to look as it vibrates. Okay? And let's say that the length of the string is a fixed thing. Let's say the tension is fixed. Let's say the mass is fixed. In other words, everything's sort of fixed. When you pluck that string, sort of right in the middle, well, what it does is it makes that wave kind of oscillate around that equilibrium point. And again, we get these regions of nodes here on the end, and then one large antinode here in the middle. Okay? But one of the interesting things that you can do is if you alter the way in which the string is being vibrated, you can change the physical look of that string. Let's look at an example here. As the string vibrates, you'll notice that we have sort of the two nodes at the end and the one antinode at the middle. You'll also notice up here that the frequency is set here for 9, let's say, hertz, whatever that unit is. If I suddenly change this to 18, well, now look what has happened. So now I have a shape that sort of looks like this. Now, in a way, there's a node here, there's a node here, and there's a node over here. So now I've got 3 nodes and 2 antinodes. Now, I haven't changed the length of the string itself. That's still a fixed amount. But now I have sort of a different looking wave. Notice before, when it was this value, I don't actually have a full wave here. Okay? This is actually only, because if you think this is the beginning, well, I'm only down here once. I've only got about half of my entire wavelength that exists here. And that's something interesting that actually happens. So if you're looking at the length of this whole string here, when I vibrate it like this, the length is only producing half of the wavelength that's available there. But if I change the rate or the frequency at which I vibrate that string, I then produce something that looks more like this, which if you now look, looks a lot like a complete wave. Let's sort of dot it like this. And you have a node, a node, a node, and now you have 2 antinodes. Now again, the length of the whole string hasn't changed. But now I'm able to produce a full wavelength. Okay? Well, what did I do? Well, clearly, in order to cut the wavelength in half, I must have doubled the frequency. Because, as we all know, I haven't changed the medium. And if the medium doesn't change, then the velocity must remain constant. And this equation, v equals lambda f, still applies. Wavelength and frequency must be inversely proportional to each other. So if I look at this example again, where this wave looked like this when I had a frequency of 9, and I double it to 18, so what I've done, without changing the length of the string, is to cut the wavelength in half by doubling the frequency. So, remember the original frequency was 9, so let's triple it. Notice, 3 times the frequency, the wavelength is now 1/3 what it was. Again, showing that inverse proportionality between wavelength and frequency as long as the velocity remains constant. So, what was I showing there? Well, it turns out that every string has what is called a fundamental frequency. The fundamental frequency is the lowest possible frequency that that string can have. In other words, there will only be one antinode within the string itself. So, again, the fundamental frequency looks like this. Okay? A node at each end and a single antinode in the middle. Now, the way that fundamental frequency is determined is with the following equation. F1, which represents the fundamental frequency, is equal to the velocity of the vibration of the string over twice the length. So the fundamental is the speed of the string's vibration over twice the length. Now, if you recall, that twice the length part is because in order to get a full wavelength, well, at the fundamental, the length is only half of a wavelength. So lambda would be twice the wavelength. So again, this is really just this same equation, v equals lambda f all over again. Now, interesting enough, if you vibrate the string the right way, as I demonstrated before, we can produce a wave that looks more like this. Or maybe even like this. Okay. In this first case, I have node, 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 antinode, antinode. In this case, I have a node, 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 antinode, antinode, antinode. These other two cases are referred to as harmonics. Now in music, they're sometimes called octaves, but a harmonic is simply a multiple of your fundamental frequency. Okay, so this one here on the left would be called F2, and this one on the left would be called F3. Notice that the number of the harmonic also matches the number of antinodes. So where the fundamental frequency of a wave is always half the wavelength, the harmonics are multiples of that fundamental frequency. And to get whatever harmonic you want, called the nth harmonic, we take that number n and multiply it by our fundamental. So if I want the third harmonic, whatever the fundamental is, I multiply it by 3. If I want the 27th harmonic, whatever the fundamental is, I multiply it by 27. But again, as the frequency goes up, the wavelength must go down by the same proportionality. In other words, if I double the frequency, I cut the wavelength in half. If I triple the frequency, I cut the wavelength by 1/3. So again, the harmonics are found by taking n and multiplying it by the fundamental frequency. So those are our two equations for strings. All right, let's look at an example. You have a 60 centimeter long string vibrating at 200 meters per second. Determine the fundamental frequency and wavelength, and then the fifth harmonic and its wavelength. Okay, well, to begin with, the fundamental frequency, v over 2L. Well, the string is vibrating at 200 meters per second. It's 60 centimeters long. And that gives us a fundamental frequency of about 166.7 hertz. Okay, now, how do I get the wavelength? Well, there's two ways you could do it. One is our good old-fashioned formula for waves, v equals lambda f. Again, the velocity is 200. The frequency, we just calculated 166.7. And that gives us a wavelength of 1.2 meters. Now, there's another way, of course, that we could have done it, which is to remember that at the fundamental, at F1, the length is half of a wavelength. So if the length is 0.6 meters, then the wavelength is still 1.2 meters. Okay, so that's a way to check it if you want to look at it that way. Now, to get the fifth harmonic, F5, well, all I do is 5 times my fundamental. other words, 5 times 166.7. And the fifth harmonic would be 833.3 hertz. Now that wasn't too hard, was it? Now, how do I get the wavelength? Well, again, sort of two ways to do it. First of all, the easiest way, probably the safe way, stick with your wave equation. Still vibrating at 200. Again, it has to keep vibrating at that same constant rate because it's a set medium. The new frequency, 833.3, gives a wavelength at the fifth harmonic of 0.24 meters. Okay? That's one way. The other way to do it is to remember that inversely proportional rule. So if the frequency increases times 5, then the wavelength must divide by 5. So if I take that fundamental wavelength of 1.2 meters and I divide it by 5, well, I still get that same 0.24 meters. Again, two ways to check it. Now, another way to produce standing waves, particularly in music, is through wind instruments. Now, wind instruments work a little bit differently depending on whether they're reed or they're something like a trumpet or trombone or something like that. But what they do is they cause the air inside these instruments to create a standing wave. In other words, the air molecules are made to vibrate, but they vibrate in a way that they create a standing wave. Now, there's two ways to look at it. First of all is something called an open tube, sort of an open-tubed instrument. And an open tube is open at both ends. And the result of them being open at both ends is you end up with actually an antinode at each end of the tube. And at what's called the fundamental, you'll have a single node, but you also only produce half a wavelength. In other words, if we have an open tube, okay, one good example is, for example, is a pipe organ. Okay, pipe organs have open and closed tubes, but particularly has an open tube. And that open tube has a certain length. Okay. Well, if I create a standing wave, the lowest possible one is I begin here, and I've got to have a full amplitude at each open end. And the only way I can do that is if my wave vibrates like this. Now, that creates an antinode here, and a node here. Okay. And you'll notice that, again, that's only half of a full wave. So it looks like the string, only the nodes and antinodes are reversed. Because the string is fixed at each end, there are nodes, but since the open tube is open at each end, that's where we're going to have our antinodes. Interestingly enough, the equation for finding the fundamental of an open tube looks a lot like, or looks exactly like, that first string, V over 2L. In the equation for the fundamental frequency of a tube, V over 2L, this time the V stands for the speed of sound. Okay. Now, there are also harmonics for an open tube. In the harmonics, if I draw my wave, my next possible shape would look like this. In other words, this is my F2. Now you'll notice that I have antinode, 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 node, node. F3, antinode, 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 node, node, node. So notice, again, the opposite of the string. This time, the number of nodes matches what harmonic you're dealing with. But equally, something else that's the same is to determine the harmonics within an open tube is also the same equation. Fn equals n, which is going to be any number, 1, 2, 3, 4, 5, whatever, times your fundamental. Again, where n can be any number we want. Okay, so that's for an open tube. Now, there's an interesting thing that you can do with tubes, and that is you can close off one end and make what's called a closed tube. An example is, again, pipe organs sometimes have louvers that open and close the tops of the tube. If you've ever seen a trumpet player who puts sort of muffler thing in front of the trumpet, that sort of closes off one end of the tube, and that significantly alters the way the wave looks. In a closed tube, which still has a certain length, well, I've got an open part here at the end, so that's where I've got to have my maximum amplitude. But then I cut it off right there. I have to cut the wave off right there. And you'll notice that now only gives me 1/4 of my wavelength. This is the fundamental of a closed tube. So for a closed tube, we have one antinode at one end of the tube and a node at the other end of the tube. So the fundamental has one node and one antinode and only 1/4 of the wavelength. Because of that, that actually alters the way we calculate our fundamental frequency. Where for an open tube, it's V over 2L, much like the string, because we can have the half wavelength relationship. Well, because now we only have the quarter wavelength relationship, the fundamental is V over 4L. Where again, that velocity represents the speed of sound. Now, something interesting happens next. If I try to draw a new wave in this tube, thus if I want to increase the frequency, well, the next possible wave I'm going to get looks like this. Now notice again, I don't have a full wave. I'm not able to complete my wave in this case. And in fact, I've only got 3/4 of my wave in that entire length. Two antinodes and two nodes. Turns out this is not the harmonic F2, this is the harmonic F3. And in fact, if I try to do the next one, okay, well, I've got 1, 2, 3 antinodes and 3 nodes. But I have, in this case, 5/4 of a wave. And so this turns out to be the harmonic F5. So what does that mean about the harmonics for a closed tube? Well, although we calculated the same way, Fn is the n times F1, all n's have to be odd numbers, 1, 3, 5, 7, 9. A closed tube can only produce the odd numbered harmonics. Okay? Makes it very different from the open tube and the string. So let's look at an example. Determine the fundamental frequency of a 40 centimeter long open and a 40 centimeter long closed tube, and then determine the third harmonic for each tube. Assume a speed of sound of 340 meters per second. Okay. So the fundamental for an open tube is V over 2L. Speed of sound, 340 meters per second, over 2 times 0.4 meters. Gives a fundamental of 425 hertz. For the closed tube, V over 4L, well, 340 over 4 times 0.4, and that gives you 212.5 hertz. Now, that should make sense because the closed one is half what the open one was. Because of that difference between over 2 or over 4. Now, the third harmonic for the open tube would be 3 times its F1, which is 1275 hertz. And the F3 for the closed tube 3 times 212.5, 637.5 hertz. Okay. Not too complicated. Now, if you really wanted to mess with someone's head, you could say, okay, I want you to calculate the 6th harmonic of each tube. Well, the 6th harmonic of the open tube would be 6 times 425, the fundamental frequency, which gives you 2,550 hertz. And then the 6th harmonic for the closed tube. Now this is where people often make a mistake. They'll start calculating something, but can't exist. There are no even harmonics for a closed tube. Okay. Now, some other interesting things about waves and sound and different things like that. One of the things that waves can undergo is a process called resonance. When an object resonates, this means that you can force an object to sort of vibrate at its natural frequency. Now, for example, one of the things you can do is take a tuning fork, and if you strike it and find another tuning fork that is of the same frequency, it will cause that tuning fork to start vibrating even though you didn't strike the other tuning fork. It's a pretty neat phenomenon. Now, one of the things that what happens is when something is resonating, it also yields its greatest amplitude. Now, that can lead to trouble. A classic example is something called the Tacoma Narrows Bridge. Now, one of the reasons that happened is because the bridge was almost made too well, and so it has what's called a natural frequency, and the wind was sort of hitting it at just the right way to cause it to yield its greatest amplitude, to resonate. Okay? And eventually that sort of led to the collapse of the bridge itself. Now, this is also the method to break glass with sound. Okay? If you take a nice, particularly a crystal glass, that has a very natural frequency, if you kind of flick the glass, it makes this very set tone. If you send a sound wave that has the exact same frequency into this glass, it will begin to vibrate at a very, very high amplitude. Now what you're going to see is this being done to a glass under a strobe light, so you can actually see the glass resonating. So you can see under the strobe light that the glass is oscillating, it's growing and shrinking because it's being hit with its same frequency, that's the frequency of the glass itself. So eventually it just can't take it anymore, especially when they turn it up really high. Cranking up the amplitude, and there it breaks. Pretty neat, huh? Alright, that's going to do it for our lectures on mechanical waves. I'll see you next time.